This blog shows how I generated this XY waveform for an oscilloscope. It was quite a journey using 9 different software packages. This is the waveform generator I used. Next time I'll find a more efficient process. The first thing I did was import an E14 logo bitmap into CorelDRAW to convert that into a structured line drawing. CorelDRAW can actually trace the outline of a bitmap, so let's try that. Here we can see that it's going to transform those fuzzy edges into multiple lines. So we want to decrease the detail slider until it's just showing a single outline. That's too far, so it's got the one actually is completely missing. So we have to boost that up a little bit. Okay, I guess that will have to do. Now we can delete the original fuzzy image. Then we can ungroup these objects. And combine them into a single entity. Note this applies the same fill to the entire thing. Now we can use the node tool to increase the number of nodes. It's just doubling the number every time I click on this little plus sign. We get lots of interstitial nodes wherever they were close to start with. If I want more nodes where they are widely spaced, I can just select the ones where I want more nodes and do that same little plus sign on the areas where there are not very many nodes. Okay, all selected. Now hit the plus button and increase. Now we need to join up all these objects so that they're one continuous line. We just use the node tool to add nodes, split nodes, and join nodes to make this happen. After joining the 4, we'll have to deal with the eye of the E and make that into a continuous line as well. The next program requires straight line segments, so this node tool accomplishes that with a single click. This then gets saved as an SVG file. In practice, I actually cleaned it up a lot more before adding all the nodes. This is what the cleaned up version looks like. Unfortunately, the SVG file from CorelDRAW fails to import into Robisco-Scopio, so I had to use Inkscape to load that file in and just resave it as an SVG file from Inkscape. Now I can simply open that SVG file in Robisco-Scopio. Now it shows the graphic and automatically splits it into a stereo wave file with the X and Y traces on each channel. I had set it up with a 10-second recording time, so it plays a lot of waveforms that will last for 10 seconds. Ultimately, I only need one waveform, so we'll have to split that off later. And we're going to use Audacity to do that. We just load in the waveform and delete everything except the first instance of the waveform. Now we need to save this waveform and then convert it to a CSV file. Next up, we're going to use a Python script to convert that waveform to a CSV file. So I'm loading the Python program into the Visual Studio Code program so I can run the Python without using a command line. It asks for an input waveform file name and creates two CSV files, one for each of the channels. Then we can edit the CSV files in a spreadsheet. This is LibreOffice Calc. I'm just going to drag in some CSV files. So this is the left channel from the previous program. And you can see it's marked left here. Now if I drag in the right channel CSV file, it's going to create a new spreadsheet. And I want to copy this column over to here. And we'll just get rid of that other sheet. So now we've got left and right. I don't really need the titles here, so I'll just delete that row. So Robisco-Scopio records a continuous waveform, so the first thing I want to do is just pick off a single instance of the waveform. Suppose I pick off about 1,000 of these just to see where we stand. So here we are at 1,000. We'll select 1,000 points and plot them. And you can see that this waveform is starting to repeat here at 960. So let's just go back and just select 960. Here's 960. And in fact, what I want to do is delete the rest. So I'll select these and just copy them to a new sheet so that I can get rid of the old sheet. Delete sheet. And we're left with just 960 points. Now if I want to plot them, I'll just plot these two rows, the XY coordinates. Let's do that. So we can see it looks like this, but if we select the XY scatter plot, you can see it starts to look like an E14. If we select lines only, it will start to look like E14. But if we select points, we can see where there are gaps between the points. So you can see there's some anomalies in the data where we got these points that we don't like. So if I do the points thing, does that, I know in Excel this would allow me to select the point here and it would show up as a highlighted point over here. This one is not so great. So we will have to look through the data to find out where these anomalies occur and just adjust the values here. But before we do all that, one thing that we need to do when we're going to plot these things is have a reasonable voltage. So these numbers actually correspond to voltage, and we want to convert them to something reasonable, say around 2 volts. So the maximum is just over 8,000 here, negative 8,000. So if we divide these numbers by 4,000, we will get something in the range of 2 volts. So let's do that. This is equal to B1 divided by 4,000. And we get 1.69 volts. And if we do that, we get this guy divided by 4,000. And if we copy that all the way down, there we go. So now we have voltages in these two columns. Now there's still a formula, so what I want to do is get rid of the formula. So I'm going to copy it and paste. Special, just the numbers. So here we are. Now it's just a number, not a formula. Oh, I should have done it to both columns, so let's do this column. Copy and paste, special, just numbers, okay. And we're good. So now we can delete these two columns. A lot of putzing around here. But now we have voltages in these two columns, and we've got the right number of points. We'll go back to plotting it out with a chart. We need an XY plot. And now it's just a matter of going in there and cleaning up. So this one is going to show us dramatically where the problems are. And we want to show in here where there's very few points. You can see the points in green here. And that's really more or less a straight line. But we need to add a bunch of points, because when this gets plotted on the oscilloscope, there will be basically big gaps if we don't have a lot of points there. So we'll just search down here for the start of these big gaps and insert some more points. So let's do that. Okay, now we want to just find out where we need to add data. So let's go in here and write a formula which is equal to if the absolute value of B1 minus B2 is greater than 0.1 volts. We want a 1 here. Otherwise we want a 0. Boom. And we want to check both columns, so copy that over here. And we're going to copy that all the way down to here. And we can see all these areas where there are 1s, we need to add points. So that tells us where to look for problems. So let's look at some places where there are a bunch in a row, like here. So over in this column, all the values are staying the same, but here they're jumping a lot. So what we want to do is, this should be a straight line because these values are not changing, but there's not very many points in here. So we want to add a bunch of points, and we're going to make them all 0.1 volts from the previous one. So these are decreasing all the way down to 0.5 from 2. So if we make this point 1.9 to make it 0.1 volts below the previous one, and just to make this an even number for the sake of an even number, we're going to be able to copy these to interpolate all the way down. So we're going down to all the way down to here. In fact, it goes down to 0.04, but we actually want a lot more points because this only gets to 0.13. So in here we're going to add in a bunch of points. Insert rows, and we're going to interpolate. Well, we're going to copy all of these down and see what happens. So these ones stay all the same, and you can see that these ones are decreasing by 0.1 volts every time, and we only got down to 0.8, so we need to add some more. You can actually do a quick calculation to show how many of these you need, but I'm just winging it here. Insert rows above and do our copy again. And we get to 0.1, which is good. So this one here, actually we can copy it down one more, right? So we're going to make that a 0. These guys, it doesn't really matter. Actually, these numbers don't matter at all. But they need to be there for the next program. So we just cleaned up this area, which is probably one of these big long straight lines here. So let's actually do a second plot to show both of these plots at the same time. So down here we're going to do a plot. Same plot, except just showing these points. So clearly what we did was just we filled in this group of points right here. So we have the two plots. One shows where these anomalous points are, and the other one is showing where we're missing interstitial points. So I'm going to go through and clean these up. Basically, wherever there's a point that's out of place, I'm going to change the values to put it in the right place. Add in a bunch of these interstitial points and show what that looks like after I've done it. It's a tedious exercise, and the next time I do this, I'm not going to go through this. I'm going to write a program that generates the proper CSV points right from the drawing so that I don't have to go through and clean this up. Okay, now I've cleaned up the plot. Obviously no anomalous points, everything is smooth, and if we look at the points, there's a few areas where I've still got a little bit of a gap, but I think it'll plot okay on the oscilloscope. So what we need to do, and what I have done, is create a left track and a right track. We want to create two files, one with points for the left track or the left, x coordinates, and one for the y coordinates. And once we export those to CSV files, then we can go and convert the CSVs to binary for the waveform generator. So here we are back in Visual Studio Code. We've loaded up our Python program. This one converts CSV to binary for this MP750-511 wave generator. So we need to specify the file we're going to convert. This is the right, the XY of the XY CSVs, and then with the binary that is needed to, or the output file that we want in binary, and we simply will run and debug this thing right from Visual Studio Code. And we simply change the name of the input and output files to do the X and Y. And that's all there is to this Python stuff. Okay, this is the waveform editor that came with the Multicomp Pro Wave Generator. And what we can do is simply open, say, the left binary file that we created from the CSV, and we can send that to the wave generator just by selecting channel 1 and writing the wave. And then that download is finished, and that waveform is over in wave generator. We can recall it, and there it is. Now if we want to do the other channel, we open the right channel and we can see it's a different waveform, and we can select channel 2 and whoops, write that wave. Okay, and we can recall it, and it comes back here. So this is pretty useful for just remotely copying files over to the wave generator. Of course, we could put them on a USB stick and stick them into the front panel of the wave generator as well. And once they're there, you can store them in the wave generator's local memory. Now you can, of course, edit these waveforms using the drawing tools up here, but I wouldn't want to try and draw this waveform and make it match up with the XY, the two traces, one for X and one for Y. So that's why we created them independently, and we're just using this program to transmit them to the wave generator. Here's what it looks like on the wave generator, and here's what it looks like on the scope.